In our previous lessons, we wrote some basic code for binary search tree, but to solidify our concepts, we need to write some more code. So I've picked this simple problem for you. Given a binary search tree, we want to find minimum and maximum element in it. Let's see how we can solve this problem. I have drawn logical representation of a binary search tree of integers here. As we know, in a binary search tree, for all nodes, value of nodes in left subtree is lesser and value of nodes in right subtree is greater. This is how we can define node for a binary search tree in C, C++. We can have a structure with 3 fields, one to store data, another to store address of left child, and another to store address of right child. As we had seen earlier, in BST implementation, identity of the tree that we always keep with us, that we pass to functions, is address of the root node. So what I want to do here is I first want to write a function named findMin that should take address of the root node as argument and return me the minimum element in the tree. And just like findMin, we can write another function named findMax that can return us the maximum element in BST. Let's first see how we can find the minimum element. There are 2 possible approaches here. We can write an iterative solution in which we can use a simple loop to find the minimum element, or we can use recursion. Let's first see the iterative solution. If we have a pointer to the root node and we want to find the minimum element in BST, then from root we need to go left as long as it's possible to go using the left links. Because in a BST, for all nodes, nodes in left have lesser value and nodes in right have greater value. So we need to go left as long as it's possible. We can start with a temporary pointer to root node. We can name this pointer temp, or we can name this pointer current to say that we are currently pointing to this node. In my function here, I have declared this pointer to BST node named current, and initially I'm setting the address of root in it. And with this pointer, we can go to the left child with a statement like current equal current arrow left. We first need to check if there is a left child, and then we need to move the pointer. We can use a while loop like this. If the left child of current node is not null, we can move this pointer current to the left child with this statement current equal current arrow left. Here in this example, currently we are pointing to this node with value 15. It has a left child, so we can move to this node with value 10. Once again, this node too has a left child, so we can go left again. Now this node with value 8 does not have a left child, so we cannot go towards left any further. We will come out of the while loop, and at this point the node that we are pointing to has minimum value, so we can return the data in that node. There is one case that we are missing in this function. If the tree is empty, we can throw some error. We can return some value indicative of empty tree. If I know that the tree would have only positive values, I can return something like -1. So here in my function, I've added this condition: if root is equal to null, that is if the tree is empty, print this error and return -1. One more thing, we do not need to use this extra pointer to BST node named current. Root here is a local variable, and we can use this root itself. So we can write our code like this. While left of root is not equal to null, we can go left with this statement root equal root arrow left, and finally we can return root arrow data, which is only an alternate syntax for asterisk root dot data. Modifying this local root is not going to modify my root in main function or whatever function I'm calling this findMin function from. So this is our iterative solution to find minimum element in BST. The logic for finding maximum is similar. The only difference will be that instead of going left, we will have to go right all the time. I leave it for you to implement. Let's now see how we can find minimum element using recursion. If we want to reduce this problem in a recursive manner, in a self-similar manner, then what we can say is, if the left subtree is not empty, then we can reduce the problem to finding minimum in left subtree. If left subtree is empty, we already know the minimum, because we cannot have a minimum in right subtree. Here is the recursion that we can write. Root being null is a corner case. If root is null, that is if the tree is empty, we can throw error. Else, if left child of root is null, we can return the data in root. Else, if left child is not null, or in other words, if the left subtree is not empty, we can reduce the problem to searching minimum in the left subtree. So we are making this recursive call to find min, passing it address of the left child, passing it address of the root of left subtree. Left child would be the root of left subtree. This second else if is our base condition to exit from recursion. If you had understood the recursion that we had written earlier to insert a node in BST, then this recursion should not be very difficult for you to understand. So here is our recursive solution to find minimum in a BST. To find maximum element, all we need to do is we need to go searching in right subtree. Okay, I'll stop here now. In coming lessons we will solve some more interesting problems on BST. Thanks for watching.